Hi, I'm Jeff Bier with the Embedded Vision Alliance, and I'm here today with Michael Tusch of Apical. Hello, Michael. Thanks for being here.
Pleasure. Hi, Jeff.
So we're going to talk with Michael about image pre-processing. But first, Michael, just tell us a little bit, if you would, about Apical. What does the company do?
Sure. Well, Apical, we started Apical up around 2001. We've been working for the last 10 years specifically on image and video processing algorithm development and implementing those algorithms in hardware and embedded software designs. We've been working on products ranging from high-end DSLRs through smartphones through to surveillance and video conferencing systems. And our main interest is in taking ideas derived from studying the human visual system to improve the quality of imagery that comes out of digital imaging devices.
I see. So this is what we might call image pre-processing, taking the raw data from the image sensor and cleaning it up and tuning it in various ways to get a better looking result.
That's correct.
Got it. So for digital camera, DSLR or otherwise, the utility of that's pretty obvious to give me a more pleasing looking picture, more natural looking picture. For an embedded vision system where the image might not ever actually be displayed, but it is rather being consumed by algorithms, why do we need to be concerned with having a better looking image?
Yes, interesting question. So I think there are a number of factors there. The first is we want, for embedded vision algorithms, we want accurate images. In other words, we want images that accurately represent the real world in terms of its wide range of illumination levels, of colors that are rendered differently under different lighting conditions, and also we want to maximize the quality of the data we're getting. For example, signal to noise ratio. We've always got noise in the system. We want to reduce that as far as possible while preserving important information from the scene. So I think accurate and imagery which reveals information about the scene is important. The other thing to consider is that the human eye and brain system is also an analytical system. The reason fundamentally why we see the world is to enable our brains to make decisions, just like the kind of embedded vision systems that we're thinking about. And so the eye and the brain do quite a lot of complex nonlinear processing to the images that fall onto our retina, specifically for the purpose of making those images easier to use by the brain. And one example is that the real world has a very high range of illumination levels. Something calls that dynamic range in cameras. Between the highlights and the shadows on a sunny day, it's a huge range of absolute illumination levels. That data requires a lot of bandwidth or memory to encode if we do it in a linear way, and also it's probably not very well normalized for algorithms. Algorithms would prefer to have a narrower range of conditions to consider. So actually the human eye does a lot of pre-processing. For example, it increases the visibility of shadows far beyond what their absolute level is before it sends that to the brain. And we might consider that kind of processing could be useful to make post-processing embedded vision algorithms either more reliable or simpler, and also to reduce the amount of bandwidth required to transmit that data between the sensor at one end and the place where those algorithms are going to be operating at the other.
I see. That's really interesting. So if I imagine like an automotive safety application where I've got maybe a front-mounted camera, as I have in my own car, looking out through the windshield, I could see what you're saying about the dynamic range, because the conditions are anything from sort of dusk with shadows to the sun bearing down directly on the windshield in the middle of the day in California, and clearly that's an enormous difference in illumination. What makes that hard? Is the sensor itself capable of, typical CMOS image sensor like might be used in such an application? Is that typically going to be capable of dealing with that whole dynamic range?
Not typically, no. In fact, those kind of scenes you described, I think automotive front-facing cameras is a particularly difficult environment under those conditions where you have rapidly changing light and also extremes of light in the same scene. And actually that that kind of scene requires a sort of a whole camera approach. It's the ability to capture the data from the entire scene depends on the optics, the sensor, and the post-processing that's applied to that data in the camera. The optics, because flare and glare can dramatically cut down the amount of useful light getting to the sensor. Internal reflections in the optical system is important. When you get to the sensor itself, most sensors, conventional CMOS sensors, capture around 12 bits per pixel, which relates to a dynamic range, as we call it, of around about 70 dBs. Now, those kind of extreme conditions, the absolute range of illumination corresponds to a dynamic range of probably around 100 to 120 dBs. So there's much more data in that scene that would be clipped away even before it comes out of the ADC in a standard sensor.
Mm-hmm.
In fact, you probably need around 18 to 20 bits per pixel to actually capture all of the information in those scenes. So there are a variety of techniques for doing that, and there are some specific CMOS technologies for actually capturing that kind of scene. But those are not common, and those are not found in consumer or lower end sensors or cameras.
Mm-hmm. So a typical cost-constrained embedded vision system might be operating on 8 or 12 bits per pixel. Let's just say we're talking exclusively about grayscale for the moment. 8 or 10 bits per pixel versus the 20 plus bits of true dynamic range in an outdoor automotive application. So how do you maximize the useful? You basically, it seems like what you're saying is the real world is 20 or more bits of dynamic range in a demanding outdoor kind of setting. The sensor is maybe getting 12 of those. How do you manage that to get the 12 bits that are going to be most useful for the downstream edge detection algorithms or optical flow algorithms or whatever's being used?
So with a conventional sensor, we have the issue of where to put those 12 bits in that absolute range, and that's where the auto exposure algorithm that runs on the camera comes in. That's the part of the camera that decides whether to increase or decrease exposure, which actually relates to typically to the integration time of the sensor. So in other words, if you go into a dark condition, the exposure time will be increased. That will mean that the sensitivity of the camera to dark information is increased. But of course, if you then take that same camera into a very bright room, it's going to be blown out. And that's the classic thing we often see in cameras, that will either blow out the sky or we won't see the shadows. So the sensor has to make a decision, and there's a lot of work in auto exposure to try to make that smooth, stable, and also get it right, to be able to get the correct exposure or the optimal exposure for a given situation. Once you've done that, you've still got the issue that typically the camera is actually only going to output 8 bits of data in the end. That's actually less than the sensor can capture, even in the standard camera designs. So you've got to map that raw data that's coming in to a standard output, which is reduced. And that's where non-linear image processing comes in. So how to take those raw pixels that come in at one end and map them so that as much information is retained within a narrower dynamic range or a reduced bit depth output. And that's where gamma correction and various forms of adaptive nonlinear processing come in. And all of those have an impact on the quality and reliability of the data that's going to come out of the back end, which is potentially then being used for embedded vision algorithms.
Very interesting. So you said the challenge is to compress the data while maintaining the maximum information. What does information mean? If I'm a human looking at a snapshot, I think I know what information means. It's sort of textures and features that I can discern as a human viewer. But for an embedded vision system where the images are being consumed by algorithms, not humans, what would information mean in that case?
So Yes, so I think firstly we've got the range of data values. So for example, quite trivially, the sensor may have around 4,000 digital pixel levels. If you take into account 3 different components, that's 4,000 per color. The output is going to be in the range of 0 to 255. So we've somehow got to map that range of values from around 4,000 down to around 255 per color without losing information. So if we did it naively, we would just clip data away and it's gone. So first of all, we have to find a way of mapping that range down. And so we have some kind of nonlinear function that will do that.
So just scaling it, just dividing it down so it fits in the range isn't a good approach.
You're just throwing away data. So that's not a good approach. If you do some kind of nonlinear scaling, you can quite efficiently map that range down. But then, of course, what you're doing is you're changing the relative values of different pixels. A nonlinear correction curve is going to differentially adjust the brightness and colors of pixels in one part of the image compared to another. So, for example, that might run the risk of affecting edges. So edges have a quite well-defined relationship in a linear domain. In the raw domain, they're an absolute difference between pixel intensities on one side of the edge and the other. After you've done some nonlinear processing, those ratios can change, and in fact they might be suppressed. So on one hand, you might be maximizing the information content in terms of the range of values that you've preserved, but on a local level, you might have smeared out very important information for analytics. So it's perhaps a more complex question of what the information you're trying to preserve is and how you do it. And there's no single answer to what's the best way of getting the raw data from the sensor to the output.
Yeah, I see what you mean. When I think about the automotive application again, I know that when I'm driving on the freeway, I sometimes have this phenomenon where even though it's daylight and the scene is well lit, the lane markings, depending on the angle of viewing and the angle of the sunlight, the lane markings can become very low contrast to my eye relative to white on black, which is how they appear in ideal lighting conditions. So I sometimes see it almost looks like the painted lane markings, the white dashed lines almost seem to disappear. And I can still, especially with the contextual cues of I know approximately where they should be, I can still detect them, but it is a little disconcerting to be driving along the freeway and then all of a sudden the lane markings almost disappear. And I can imagine, obviously the human visual systems evolved over millions of years to pick out these kinds of nuances, because it's been important in our evolutionary history to have very good visual acuity. But for an automated system, it seems like this is the kind of problem you're talking about, right? You have a lot of light, high illumination in that situation, but the contrast that between one side and the other of the edge you want to detect on that particular lane stripe is actually quite low because of the glare.
That's correct. It's a challenging problem. And in the other extreme, where you have low light, you've got the issues of signal to noise. We have them with our eyes, but we have them particularly with electronic imaging devices, where the sensor may be very noisy. Under those conditions, the image textures or the details that you're trying to pick up may be at the same level as the noise. So you've got the question of what can you do about that. You can obviously improve your optics, improve your sensors, which is costly and may not be practical. You've also got the domain of digital processing. How much can you do to reduce noise digitally? And there's a very well developed fields of noise reduction, both temporally and spatially. But those algorithms themselves have issues. You've got to suppress noise, but you've also got to make sure you don't introduce artifacts, you don't blur information, either spatially or introduce motion blur, which will affect edge detection algorithms. So there's also a balance to be taken between maximizing your signal to noise ratio and affecting the quality of the raw information that's being received by the front end.
Really interesting. So I know we've touched very, very briefly on the human visual system, and I know there's been a lot of research into the human visual system and how it's tuned for to adapt to certain kinds of situations and detect certain kinds of features, motion, and so on. How much of what is done today in cameras is in some way, inspired by or modeled on how the human visual system works? To me, it's sort of fascinating to think about. We're building these embedded vision systems, in some cases to replace human operators and relieve them of tedious tasks like watching security cameras. In other cases, to augment the abilities of human operators. And I'm curious to know to what extent in that front-end processing of capturing the image and processing it so as to maintain the maximum information content, how much of that is typically done using techniques that are modeled or inspired by what's going on in the human visual system?
Yes, it's a very interesting question. I mean, the eye and the eye-brain system is doing a lot of image processing, and I think we can separate that into processing that's actually extracting information between, like edge detection, which is really in the embedded vision domain. That's also done by the visual system, and then the what we might call just the kind of processing that affects how the images look. One thing we just talked earlier about is dynamic range and normalizing of extreme lighting. That's something which the eye does very well, and researchers have tried to really copy that. And I think the best algorithms are quite closely based on the way the eye works. I think the other important area for vision, computer vision, is color. So the eye is extremely good at correcting colors in different conditions, better than I think than any device that's been made yet. So the example is, we're used to walking around and we're seeing objects in completely different lighting conditions. Artificial light, indoor light, changes of the quality of outdoor light between day and evening and night. And we tend to see whites as approximately white and blue as, but the absolute light that's coming off those surfaces is totally different. And to a sensor, the colors that are coming out, I mean, just if you think about it, a CMOS sensor has a color filter array on it. It's got one color per pixel, so it's a pixel either a red or a green or a blue. So first of all, we have to try to reconstruct what the color of each pixel is by interpolating the neighbors. So we're trying to guess what the actual color is, and then that color may actually not reflect the true color in any way. For example, under some artificial lighting conditions, a white shirt and a blue shirt will look absolutely identical to the sensor. They will receive the same digital information. So one thing that cameras try to do is copy the eye in the way it's able to get correct colors under a very wide range of conditions. That's called auto white balance, typically. And again, although many embedded vision algorithms don't require color, many do. For example, face detection might involve a skin tone analysis. So therefore, getting accurate colors from an optical system which really doesn't have enough information to know what the accurate color is also quite a complicated problem, I would say.
Very interesting. The Microsoft Kinect has been very, very popular and has really helped to build awareness, both with consumers and with engineers, about the possibilities of embedded vision. And one of the things that the Kinect does, in addition to the gesture-based control of games, is it does face recognition to distinguish users, so that when you walk up to the system, it knows that's Michael and not Jeff. And then also, when you have two players playing a game, it uses face recognition to distinguish between them, even though they might exchange positions. And one of the things that I've heard is that sometimes the face recognition isn't always reliable, and perhaps we know it's a pretty low resolution sensor, the 2D sensor in the Kinect. The lighting conditions are typically pretty poor in your typical living room where people are playing games. So I wonder if it's suffering from the very same problem that problems you just described with dynamic range and color detection.
quite possible. I mean, again, I don't have any insight into exactly how the Kinect is imaging faces, but you're absolutely right that the indoor living room environment is in some respects quite controlled. It's definitely not as difficult as the automotive case you described, but there are significant variations in lighting between whether you might have a window and it might be daytime, it might be nighttime, you might even be in a situation where the only illumination in the room is coming directly from the TV, and the color of that light may depend on what you're watching. So both in terms of absolute light levels, that's not necessarily an easy environment. It may be dark. That means the sensor, which is probably not a very expensive sensor, may have signal-to-noise issues. So you may have difficulty measuring image against noise background. And color, if skin tone is being used or any other color cues are being used, that environment. There will be situations, I'm sure, where the auto-white balance doesn't work very well, and those might contribute to the corner cases that are being seen.
Really interesting. So, what, in an embedded vision context, what's challenging about implementing algorithms for things like auto-white balance, noise reduction, and color correction in an embedded context where we have limited processing power, limited memory?
Yes, I think probably the main factors are that the algorithms that are required are complex. For good noise reduction or good dynamic range processing, a very large number of filters being applied. So the designs are quite complex. So if it's a hardware design, that's going to be significant silicon area. If it's embedded software, you've got the load on the processor, and that's particularly difficult where you have high data rates. So some applications don't require high frame rates or high resolution sensors, but many do. The 1080p is becoming standard, and obviously higher frame rates are becoming important for traditional cameras. So that's actually pushing quite a lot of data through a pipeline. Mm-hmm. So the image processing pipeline is a sequence of transforms that happen, but that has to happen for every pixel, for every frame, continuously, and you can't really afford any latencies in that. So in other words, it puts quite significant constraints, and I think people in this area are very familiar with constraining their algorithms very strongly to meet the requirements of low power and high data rate and so on. So we're very used to looking at algorithms which produce fantastic results in the lab, but then having to really shrink them down to make them practical. And that's probably the most interesting area for one makes a practical algorithm for these kind of devices.
Now, is it typically feasible? Let's just say we were talking about a 1080p sensor, 60 frames per second, which is becoming mainstream. Is it feasible to implement algorithms like we're talking about here, white balance and dynamic range management and noise reduction, in a sort of typical programmable processor, a CPU or a DSP, or because of the data rates, do you need more specialized hardware?
I think the answer is that, I think generic CPUs that we find in embedded systems, it really exceeds their capabilities considerably. So you have to look at accelerated processors. So that might be DSPs, it might be GPUs, it might be other kinds of dedicated hardware. I think what tends to be found is that to achieve the performance levels that are required for multiple applications, even with acceleration, you tend to max out the processor quite rapidly. In other words, you end up using almost all the resources you have to get your core performance, which is fine, but it then doesn't really leave anything for other things that you want to use that processor for. So, so what most semiconductor manufacturers, they've gone down the line of some level of dedicated hardware video processing. In other words, the algorithms that are relatively stable in terms of development if possible, they'll be hardened, and that will then remove the load from the processor and allow that to be used for perhaps more advanced or more evolving algorithm developments.
So very very special purpose, fixed function hardware for implementing things like auto white balance and noise reduction and dynamic range management is the typical approach for where you have reasonably high resolution, high frame rate sensors.
Yes, I mean, I think the drivers are high resolution, high frame rates, low power and low cost. I think if those come together, I think traditionally, well up till now, the default approach has been to harden in hard logic. Of course, it's quite possible to do these things on FPGAs and then embedded processors like DSPs. Those tend to be found more in the higher end, less cost sensitive, less expensive, less power constrained environments.
To what extent are people integrating these kinds of front-end processing steps very tightly with the sensor itself, either on the same actual die as a CMOS sensor or in the same package as a front-end processor integrated in a package with the sensor?
It depends, I think, very much on the sensor technology and on the application. I mean, there are two different trends. I mean, one is increasing resolution of the sensors. There's other is reducing cost of the system. Fundamentally, you've got the issue of geometry. Process geometry for sensors is much higher than, for example, application processors. So the cost of logic on a sensor die is much higher than it is in a digital processor. So that usually drives more complex image processing to go off the sensor and into a secondary processor. That's not always the case, but that's a significant trend, particularly in consumer applications. But there's a mix. There are sensor SoCs, where you combine the sensor itself and an image processor on the same die. There are dedicated companion processors where you do specific processing on a separate device. That could be an SoC, could be even an FPGA, targeted to the specific characteristics of a given sensor. And then there are the generic image processors, which can handle any kind of sensor. And those all coexist in the market.
And then it sounds like in many cases, as you were saying earlier, you might have an application processor with a dedicated coprocessor integrated into the application processor for doing the image front-end work.
Yes, that's right.
So
you have a mix of generic CPU, you may have DSP, you may have GPU, and you usually also have some kind of hardware engine for the front-end video processing.
Very interesting. So we've talked about white balance for getting correct colors. We've talked about dynamic range management for handling very widely varying illumination levels. We've talked about noise reduction. What about image stabilization? This is something, again, that the human visual system does, so well and so effortlessly that we're pretty much unaware of it. But then when you take a video clip with your smartphone, it doesn't really have a natural way of holding it steady, and you look at it, you sort of get motion sick, and you think about a set of vision algorithms trying to work with, that very jittery image. That seems like a big challenge. So I would assume that image stabilization, while valuable for my camcorder, so that my handheld videos aren't so jittery, would be even more valuable for vision applications.
Yes, I think that's right. I mean, in a sense, vision algorithms like object tracking, of course, they're looking for local motion against a background which may or may not be moving. So in theory, you could construct algorithms that are less sensitive to global motion. But it seems from our research that eliminating global motion is very helpful in providing good data for subsequent vision processing algorithms. And for exactly the reasons you described. There are two kinds of motion in the system. One is noise, actually. I mean, temporal noise is a kind of motion, and any kind of algorithms that are based on pixel motion are going to be affected by temporal noise.
Temporal noise, I'm sorry, just to clarify, is a given pixel sort of flickering, not based on the actual scene, but based on noise in the system.
Correct.
Okay.
So that can be smoothed out in time quite effectively. The other is, as you mentioned, is camera shake. So again, many of the applications we'll be looking at for embedded vision will be fixed camera, but of course if it's an outdoor system, you may have a high degree of vibrations from noise and so on. And if we're talking about augmented reality, yes, absolutely, handheld cameras are all subject to shake. Two approaches to that. One is optical stabilization, so you can actually stabilize move the sensor against the lens, and that's used in high-end cameras. That's extremely effective. That's the best way of removing shake. It's expensive though. You can also do this digitally. So what you can do is you can extract a global motion vector from a moving scene. You can track specific parts of the scene and look for how they move, and that will allow you to estimate the direction and rate of motion, and that can be both translations and rotations. And you can then correct that. You sort of warp the current frame so that it fits over the previous frame. Mm-hmm. And that has a very strong effect in stabilizing the video. So that technology can be very useful. What it will do is it will ensure that your background is totally stable, even if the camera is actually shaking strongly. Mm-hmm. And that means that removing that background motion is a stage that you don't have to do in your vision algorithm.
Right, yeah. So a lot of vision algorithms sort of assume a static background, right, and use the fact that the background isn't moving to distinguish between the foreground and the background. So if the background now is moving due to vibration or camera shake, then that could be very confusing to those algorithms. So the way you describe it sounds pretty simple. Extract a global motion vector and then adjust the image, but I have a feeling that there's some tricky implementation aspects of that.
Sure, it's certainly non-trivial to make that kind of algorithm work well. How you extract that motion vector and how well that works in different corner cases is important. And what you've got to be careful of course, is that you're legitimately extracting global motion of the camera, but you're not being fooled by locomotion. So if somebody walks in front of the camera, you don't want to artificially detect that as being global motion, because that will actually make your camera perform worse than if you didn't have it going at all. So certainly that's not a trivial problem to solve, but I think it's a fairly well understood and it can be handled pretty well by the current algorithms.
Once you have the motion vector, is there computational complexity associated with adjusting the frame to offset the motion vector? I'm thinking from my experience in video compression, for example, about whether you have to do things like subpixel interpolation if you can't assume that the displacement happens to fall on an integer pixel boundary.
Yes, it must absolutely be subpixel adjustment. I think you've got two challenges there in an embedded system. One is you've got the actual computations you need to do. The other is just the data bandwidth, the access to memory and back. So anything which involves acting on an entire frame at once, as opposed to being able to pick individual pixels out, adjust them and put them back, is going to be expensive in terms of memory bandwidth. So that's often also a constraint you have, especially as we talked about quite high data rates, maybe low power requirements. You've got to think carefully about how often you need to move pixels to and from memory, and that's another factor that affects the viability of those kind of algorithms in the systems.
Really interesting. So it's sort of an interesting case here where, if I understand you correctly, I think what you're saying is video stabilization both benefits machine vision algorithms by removing the vibration or camera shake and the complexity that would add, and also actually uses uh, embedded vision techniques to do the stabilization by analyzing the scene to understand, to determine what the displacement was due to shake or vibration frame to frame. Is that right?
That's correct. And that's an interesting point, that there's actually that's where the boundary between front-end processing and vision algorithms perhaps is blurred.
No pun intended.
That's right. Hopefully not blurred. Actually, yes, you're absolutely right. And actually, there's another example which is perhaps even closer, which is in temporal noise reduction. In other words, what we'd like to do there is effectively we want to be able to track motion. We want to be able to apply stronger averaging of pixels in time in parts of the scene which aren't moving.
Right. Because
there, of course, we could maybe average over 10 or 20 frames and increase our signal to noise ratio very substantially. Whereas, of course, if we try to do that with moving parts of the scene, we'll blur it. So actually, all temporal noise reduction is based on trying to detect object motion and apply different levels of filtering for fast-moving versus slow-moving objects. So really, the best algorithms of that kind are ones which are able to accurately extract local motion within a scene. And that's, of course, a classic challenge for embedded vision. Of course, they're very good algorithms for doing that, but they can be quite expensive to implement. So that's another area where the kind of algorithms that you might be implementing for embedded vision might be shared between front-end processing and decision-based part of the system.
Right, right. So you might detect, you might be trying to detect motion in order to do noise reduction, while you're also trying to detect motion because it's an object tracking based application.
Exactly.
Very interesting. Well, this has been really, really fascinating to delve into a little bit of how the front end processing works in capturing images and video, and how that can influence the latter stages, heuristic algorithms that are trying to extract higher level information and make decisions, and then also to see how some of those sort of same higher level techniques actually can be used to benefit the front end processing. So let me thank you very much for taking the time to speak with us today, and hopefully we can have you back and explore other topics and drill down into more detail on some of these things. But for me, it's been really fascinating. I think I've gotten a new appreciation for the complexity of getting a good image into the what we normally think of as the embedded vision processing part. Sounds like that front end is substantial, has substantial sophistication and complexity in and of itself.
Well, great, Jeff. I'm glad that was helpful, and pleasure to talk to you.
Thanks again, Michael. And thank you for joining us. Please come back to www.embedded-vision.com, where you'll find new videos on a regular basis on many technical topics related to embedded vision. In fact, we have one we just posted last week on image sensors by Jose Alvarez of Xilinx, talking about some very related issues about the different ways in which image sensors organize their data and different kinds of interfaces they use. So if you're interested in this kind of front-end aspect of embedded vision, you'll probably find that one interesting as well. Thank you very much.